Good afternoon. I hope I can keep you awake. Thank you so much for this invitation. It's great to be here. Thanks to David and to all the organizers. And I must say I'm kind of frustrated because I saw so many beautiful subjects I would like to work on, and unfortunately, we all have finite time. So today, why am I here? That would be a good question because I'm not working on turbulence for a long while. And that I have to be candid about this. But I think back then, in the early 2000s, together with Steve Orsag and colleagues, which I will mention later, we developed an approach to fluid turbulence, which I think has some possibly interesting idea also for the community. And in addition to that, the second reason why, sorry? The second reason why I think there might be a scope for this talk is because I feel that the work isn't finished. So maybe some of you could get some brainwave and in fact, meet the losing ends, which in my opinion are still there. So the idea is how do we how do we approach the turbulence problem using kinetic theory? So I assume everybody's familiar with turbulence models, but nevertheless, just the two words. So we have the flow field, and I'm talking incompressible homogeneous turbulence to begin with. This is the actual velocity field, which we split in a large-scale component that we can put on our computer, and a fluctuating component prime, which we cannot, just because our computers are not infinite. And of course, by definition, if I take some bracket, the velocity field, whatever this bracket means, I will get, of course, the coarse-grained field. Now, when I do this simple exercise and I apply to the Navier-Stokes equation, of course, I get some extra force, some extra term, which is basically the divergence of the correlation tensor of the fluctuation, also known as Reynolds stress tensor. And after all, it doesn't look too bad in principle because this is just a second-order moment. All right, we have tensor indices going along because A and B, actually, I forgot to put, they run over the space dimension. So this is a second-order tensor. And the question is, how do I solve for this Reynolds tensor so that I can solve my coarse-grained equation? It looks not too terrible, but the fact is that, in fact, the immediate reaction is just to write down an equation for the third-order cumulant, and this generates an open-ended hierarchy, which is never closed. And the reason why you cannot close it is that you don't have any smallness parameter. In fact, the smallness parameters is the Reynolds number, which just for a trivial, say, for a car, is 10 to 6, 10 to 7. So there is no surprise that this is, in fact, a tough problem and still keeps us busy for, I would say, more than 50 years now. So a very powerful idea, when you cannot go the hard way, you try to go heuristically. I'm afraid this is not my last presentation, but too bad, my fault. Anyway, the powerful idea dates back to Boussinesq, and the idea is simply to borrow from kinetic theory. In kinetic theory, we know there is scale separation between the molecules and the fluid degrees of freedom. So how about expressing this unknown quantity empirically through effective viscosity or eddy viscosity, which actually you can just check dimension is correct, which basically correlates the unknown tensor with something that you can compute because this is the strain of the large-scale field that you have available in your simulation. And this empirical assumption went a long way. It's a powerful one, except that there is a little flaw, which is inescapable. Whether it's serious or not depends on the problem, but in principle it is there. You cannot escape, and I can show you that in a moment. So this is the Kolmogorov, and this is, say that this is your Kolmogorov scale, and your computer is not big enough, so you have to set up a cutoff here, and you have to state that the largest small eddy, this one, largest small eddy, is too small for your computer to capture. Yet, the smallest large eddy, this one, you can retain because it's slightly bigger than your cutoff. And the assumption is that the interaction between the two still is described by an expression which heavily relies upon scale separation. Cannot be true. Okay? So no matter what you do, if you coarse-grain the Navier-Stokes equation, and you appeal to the notion of eddy viscosity, which somehow you do. The expression of the effective viscosity may change depending on the turbulence model, but this scale separation is always there. So no surprise that people thought of doing something different, and namely taking the problem of turbulence model from a point of view of within a framework where scale separation is not needed, and kinetic theory is just precisely that framework. Question is, how do I formulate the kinetic theory for the turbulent eddies? And this you don't find it in textbooks. So, I'm really sorry. I kept downloading different versions, and this is really one of the earliest ones. Never mind. I will say in Word. Okay, I have to go back. Too bad, my fault. So I think I still have the essential. And the essential is the following. Well, the first thing I should say, and there were slides here, that this is not a new idea. The idea of applying actually diagrammatic techniques to the Navier-Stokes equation dates back to Wild, to 1961. And Wild, in fact, and there is really a serious analogy with Feynman diagrams in QED, but the formalism is beautiful, is exact, but it's really hard to make something concrete out of it, just because you generate, again, a very complicated hierarchy, and you cannot close the hierarchy because in QED, the smallness parameter is 1 over 137, so it's small, and in Turbulence, again, the smallness parameter is 1,000,000. Or in your case, I think is 10 to the power 10 at least. So, that is, back in 1999, and I have really to give credit to Dong, Chen, and Steve, I've really learned from them. It was a good fortune for me to be around. The idea was, how about we postulate an empirical kinetic equation for turbulence, and the simplest possible one, a model kinetic equation, which is called BGK. I don't know whether you're familiar with BGK, but BGK is basically, this is even more complicated, is an equation in which the collision operator is just basically a relaxation term. This is the frequency, and very often you just need a single value, and you relax the distribution function around the local equilibrium and think of a local Maxwellian, okay? So you don't need to deal with the terrible complexity of the Boltzmann operator, which takes into account the details of molecular collisions. So the idea was to postulate, if you wish, a kinetic equation, which, by the way, was around for almost 10 years because we started the lattice Boltzmann in the 90s. But let me explain the philosophy. So you have a common ground, which is kinetic theory. And the way you go in the textbook is very well known. You apply the Chapman-Enskens, Boltzmann number takes you to Navier-Stokes, where the relevant variable is the velocity field. So you go from a probability distribution in phase space, 7 plus 1 dimensions, to a field theory in 3 plus 1 dimension. And eventually you filter. So you go to the Kolmogorov scale up to the delta, which is the smallest scale you can afford on your computer, and you generate a coarse-grain equation for the capital U on the hydrodynamic branch of this picture. And that's what you find in the textbook and in the papers. Now, how about just reversing, swapping the two coarse-graining operation? Instead of generating Navier-Stokes equation, you generate an eddy kinetic equation for Boltzmann. Let me call it super Boltzmann, just to have fun, okay? Capital F would be the distribution function, which describes, actually, the distribution function of the eddies which make up turbulence, okay? And this is a filtering operation, which I call projector along X, because X is configuration space, as opposed to Chapman-Enskens, which is basically projection plus asymptotic in velocity space, okay? So I generate the coarse-grained Boltzmann, and only after this is filtering, and this is Chapman-Enskens as applied to the coarse-grained Boltzmann. Now, if scale separation would hold, you shouldn't see any difference, okay? So eventually, this exercise is just a circular loop. You end up with the very same turbulence model that you would generate by coarse-grained Navier-Stokes. But I just told you that you should not, and you cannot assume the scale separation holds. Certainly, it doesn't for the eddies which are close to your numerical cutoff. So in principle, going this kinetic branch should generate new turbulence models which have no counterpart if you average Navier-Stokes. And that's basically the idea, okay? You can formulate in terms of, if you want to be abstract, if there is a commutator with these two projectors and the commutator is not zero, but we are not interested in that. So this was 1999, but here we did the exercise for a simple case, just a box. Okay, this was homogeneous turbulence. It was, I would say, a rather nice exercise, but still rather theoretical. This is the idea. Let me again stress the real point, the major point. Suppose you want to do things in terms of the normalization group, which I'm not good enough to do, and I hope some of you is, because this formal procedure has not been carried out in full, and that's one of the points where one of the loose ends, in my opinion. So if you rescale space and time by a factor b, you leave velocity unchanged because the velocity is x over t. The question is, by the time I do discourse graining, okay, molecules, eddies, and large eddies, how does my mean free path scale under this scaling transformation, given the fact that since I'm averaging over a nonlinear equation, there will be contribution to the mean free path by the Reynolds stress tensor. But you don't know, actually, how they go. And you know for sure that this alpha is greater than 1, the mean free path will get larger than linear. And then, I'm back to the point I was making before, then the chances are that you cannot assume that the Knudsen number from here to here is small enough to take the hydrodynamic limit. That's the whole point, okay? Now, this is not a talk on lattice-Boltzmann, but lattice-Boltzmann was instrumental to test the idea because you needed a tool to, just go beyond analytics. And this is an old slide. I promise for men, now lattice-Boltzmann is pretty old by now. Some of you are younger than lattice-Boltzmann. Was born basically 30 years old. Huh? And even me, I was young at that time, believe it or not. And for almost 10 years, I invariably would get the question, are you really solving Navier-Stokes? And without any really good faith, people did not believe. And in a moment, you would not believe it either. If you go to a conference in fluids, still today sometimes, and you say that you're using Boltzmann to do fluids, they ask for a sanity check. And they sympathize with that in principle. But as I'm going to show in a moment, it looks like total suicide, but it really is not. So it's worth to give you a few crash course in lattice-Boltzmann, 5 minutes. Of course, if you want details, I'll be more than pleased. It is very simple. You cache on universalities, as you always do for fluids, okay? And believe it or not, this is a real gas. And if you squeeze, in fact, if you crystallize your molecules such a way that they have only rights to move along the direction of this lattice is not a joke. This is what you use actually to do 3D simulation. Okay? It's not a cartoon. And you can count, these are 18 speeds plus a spectator, so it's called D3Q19, three-dimensional, 19 discrete velocities in 3D dimension. So this is a formal writing, but essentially that's it. I mean, you say that instead of having freedom of moving everywhere, you put your fluid on a crystal, and if you choose the direction properly, you can compute the low-order moments of your distribution, which are the one relevant to hydrodynamics, by quadrature, and the quadrature is exact. There is no error here. This is exact. It's called Gauss-Hermite quadrature. That's basically what it is. Lattice-Boltzmann is more general than that, but we owe a lot to this Gauss quadrature. And, okay, don't go through the equation, doesn't really matter. I tell you with my hands. Suppose I am a right mover, okay? You see it on there. I'm blind. And this theory borrows a lot from lattice-gas cellular automata, Frisch's, Lacour-Moore. They were really the predecessor, and in my opinion, they will come back. Not before long. So if I'm a right mover and I'm blind, when the click comes, I just move right. And if I'm a left mover, I just move left. These are not particles, these are states, okay? So this is statistical distribution. Now, take the receiver point of view. I'm sitting here, and as the next time step, I'm receiving a contribution from the left and one from the right, and then there has to be some exchange, because otherwise I have a free bunch of particles. I don't have a fluid. Fluid means collective interaction. But one of the major breakthrough of the theory was that you can put actually you can formalize the collision just like a relaxation around a known local equilibrium. And this turned the exponential complexity of the lattice gas into a quadratic complexity. This was really a breakthrough, computational breakthrough. And by now, BGK is just a value. The matrix is diagonal. And there are many reasons why this scheme is, in my opinion, is really a paradigm for complex moving matter, not only turbulence. Actually, for the last 10 years, I've been busy mostly with slow flows. But again, if I have to tell you one thing about lattice boson, the little secret about lattice boson is this. Think of Navier-Stokes, U grad U, means that you have a wild horse to ride because you move the velocity field along the trajectory which is defined by the velocity field. And in a turbulent flow, the horse is very wild. Velocity changes very wildly in space and time. Same is true in a foam or any complex flow. In lattice boson, just because you did the silly thing of working in 6-dimensional space, but this buys you an enormous advantage, the fact that the information is always transported along a crystal, along straight lines. No matter how complex your emergent hydrodynamics, that will not change a minute the fact that all your information move along the crystal. Take the most turbulent fluid, it will still move information along the crystal. This is an enormous far-reaching consequence, especially when you have a low viscosity. Why? Because we have, thanks again to the lattice gas cellular automaton, this operation in the computer is a memory shift. There is no round-off error. This is exact. The lattice gas would be exact even here. They formulate a Boolean dynamics for hydrodynamics. This we lost. But we are still machine round-off accurate. Steve Orsa called the lattice boson the antispectral method because spectral methods are known for their accuracy, virtually infinite accuracy. Lattice boson is poor guy. It's a second-order method at best, if you don't screw up the boundary condition. But it's a very good second-order method because it has exact streaming and machine round-off conservation on the collision. So in fact, we could simulate in the early days 2D turbulence and getting results comparable to spectral methods, which you cannot do with the standard finite difference. So I'm not here to make a long story about lattice boson, but I just wanted to tell you why it provided, in fact, the good computational framework to test the idea of the turbulence modeling. And last but not least, the fact that you move along straight lines makes the handling of complex geometry conceptually simple, which doesn't mean that you don't have to put hard work. You do have to put hard work, but by the time you do it, you are guaranteed to get good results, and especially parallel computers. I'm afraid the geometry is no big deal for you, as far as I can tell from what I saw today. The day it becomes a problem, I think this point is really, to us, it was crucial. To us means designing airplanes where the geometry, no spherical cars at all, okay? Okay, and finally, last but not least, since again we are working in a 6-dimensional space, although we discretize it very economically, pressure is just carried on the back of the distribution function as any other field, so we never have to solve the Poisson problem for pressure, which is 90% of the computational cost in an incompressible simulation. So very quickly, but just to give you an idea why the framework was a good one, and Steve Orsa, I will never forget that he was really enthusiastic about this because this basically, as you probably know, he was the main force behind the spectral method. But with the spectral method, he could not pursue the program in complex geometry because spectral methods, of course, have limitation when the geometry is not periodic. So here is the game. This is the same BGK equation I showed you before with a little twist, though, which makes the whole difference, that the viscosity is no longer a parameter. You promote the relaxation to the status of the dynamic field, okay? So omega is now a field, and the field, I call it turbostat because it's supposed to probe, in fact, the turbulent environment. So omega 0 would be the inverse of the molecular collision time, and this function psi, which is supposedly universally, hopefully so, will depend actually on the relevant time scales, which is k over epsilon, I should say, or omega is epsilon over k. So this is the turbulent kinetic energy. This is the kinetic energy dissipation. And this is the shear. So if you are in an homogeneous condition, the shear disappears. And what you have to do is to find this expression and then run the engine by moving in time the kinetic energy and the kinetic energy dissipation through a set of additional equations, and that closes the cycle. Okay? Now, I will return later on that. It works, believe it or not. This is a paper that we had long ago where we just stated the principle. This is a real calculation by a company which is called EXA Corporation. It was out of Boston. Now it's part of the Dassault Group, so they have been made it to the, they've been acquired by Dassault. And this is the type of calculation that one could perform. This is not my calculation. There's no way I can set up this geometry in my group. But just to give you the feeling that what was computed was really complex and very, very complicated flows, particularly, the movie doesn't work, but never mind, particularly when you're close to the wall, when you're close, in fact, to the complex surfaces, in which, in fact, the large eddies are themselves time-dependent and dynamic. So there is no real point of saying that they are in local equilibrium. That really is a typical situation when the strain, which is basically proportional to the shear that you have around the wall. This is a dimensional parameter. When this dimensional parameter is not much more than 1, it means that even the large eddies are not steady. And for instance, there is a very popular model in turbulence model called Reynolds average Navier-Stokes equation, where they assume that the turbulence is statistically steady. You would never get the time dependence of the large eddies using this model. So, oh, sorry, I have to go back. So now I will skip. Let me go now to the point of criticism, okay? The point of criticism is that these two equations were derived based on a previous calculation, mainly by Victor Jacot and Steve Orsag, which was itself derived by renormalization group treatment of the Navier-Stokes equation. So there is a conceptual inconsistency here because I made a big fuss about the kinetic approach to turbulence, and then I'm importing information from actually coarse-grained hydrodynamics. So in my opinion, there is still work needed to derive this equation or similar equation so that the framework is sound. You use an empirical kinetic equation for the eddies. The relaxation parameter has to be a turbostat, has to probe the turbulence, but then you have to close it with the equation for the main turbulent observables, which is the kinetic energy in the fluctuation and its dissipation rate. So the exercise is, can we derive this out of the Boltzmann equation? I tried. I'm not good enough, I know. I think the young Steve Orson could have done that, but I met Steve first time when he was about 50 and was already much too busy with other things. It takes a lot. I think some young guy or young of any age could do probably this work, namely close this system. In my opinion, this is still open. And Nigel, maybe we have to discuss that because I think you could be in a good position to do that. Now, there is a statement by Frank Wilczek which I like. I don't know whether I wrote. I keep going the wrong way. I'm sorry about that. Okay, never mind. No big deal. So it works in practice, but how about theory? Okay, so I like that statement. And the theory is just what I told you, in fact. Now, how much time do I have? Okay, so more than I need. So this is, I didn't even want to show because just for the purpose of this workshop, I tried to put myself back into the mood of generating something new. It's probably just the beginning of a calculation which might make sense. What I think one should do, and I hopefully will try to do it after the workshop is finished, if I take this expression and I coarse grain it, okay, I certainly generate a correction to the equilibrium due to the turbulent fluctuation. Well, let me actually explain it in a different way. because that's what really should be done. And the credit here goes basically to Victoria Cote. I think if there is a theory to be developed around this idea, a promising candidate is the idea of a theory of double fluctuation. Namely, I take the molecular velocity, okay, and I split it as a fluid velocity plus a kinetic fluctuation, which contains thermal and contains also non-equilibrium contribution. If the flow is at equilibrium, this will be basically the thermal speed. But then I add on top of this the turbulent fluctuation, which is capital U plus U prime. So I have two types of fluctuations. And when I do my coarse graining, I will have kinetic, turbulent, I will have cross terms. And at equilibrium, actually, I know how to compute them because at equilibrium, this is a temperature. The correlation tensor of the equilibrium fluctuation is nothing but the temperature times identity. And if turbulence were homogeneous and isotropic, the analog in the case of the turbulent fluctuation would be just K. The question is, what happens out of equilibrium? And it turns out that if you do this calculation using the kinetic theory, you can recover a lot of terms which really look like nonlinear turbulence modeling. So the point is, doing the perturbation, the Chapman-Ansel work on the eddy lattice-Boltzmann delivers actually nonlinear turbulence model, which were known before, and some new ones as well. So formally, I think, but again, I really would like to see this calculation done, I wouldn't say rigorously, but I mean, within a closed mathematical formalism, you define the capital F as the original Boltzmann. This is Boltzmann, not eddy-Boltzmann. And this is a probability of observing a fluctuation U prime once the coarse grain field is capital U. And we know that in homogeneous incompressible turbulence, the one-point fluctuations are Gaussian. This is, I mean, it's a safe assumption. Under this assumption, you know you can perform this integral because it's a convolution of Gaussians, and you end up with a coarse grain equilibrium, which is nothing but Maxwellian, but it's a Doppler broadening. So the effective temperature is the temperature of the molecules plus the temperature of the eddies, which is K. Then what you should do is to define, this is easy, you define the kinetic energy, fluctuating kinetic energy as a U prime square, double average, and write down an equation for this. You can do that. And Udong Chen, and so that's what you should do, write down equation for these closures. And basically, if you do that, you generate, in fact, turbulence models similar to what we had been using in this calculation. Sorry, I keep going the wrong way. If you look into the paper, that is the expression that we have been using that X has been using to do his simulation and car design and airplane design. It's an expression which comes, again, from the renormalization group treatment of the Navier-Stokes equation. Homework, derive this out of the eddy lattice-Boltzmann. I think, actually, I'm doing this homework. I get something different. I don't show you because I don't trust my calculation, okay? But I think it's an interesting point because this is a tough cookie. Unfortunately, I mean, I know for sure that you get expression. The structure is this, but the amplitudes, the coefficients matter a lot, okay? And no, this I don't dare to show because it's really very wild. So there is, in fact, a coefficient in front of this expression, which is 0.09 in what Yacotte and Orszag derived. And what I get, but again, I might be wrong, is a KT square, and the coefficient is 1. So just to say that I think there is still work to be done. I now see how it should be done. I'm not sure I am good enough to do it, but it would be important to close conceptually the cycle, because I think the idea is sound and powerful because, again, lattice-Boltzmann is doing it's really an efficient tool to test your theory. I would like to finish, but this is never enough, I mean, cannot be overstated, that it all works provided you can, in fact, generate proper boundary conditions. So geometry here is the main driver of complexity. Okay, and I used to work with X in the early days when we had to formulate basically the theoretical foundation. But when at some point I stopped because I remember I saw the algorithm to generate the boundary condition for turbulence, and it is a report that thick. I mean, it's really hyper detailed. But really, in the bulk, more or less, you're always forgiven, but not around the boundary. And in the boundary, in fact, you definitely need local adjustments of this turbostat. And again, that's another part of the theory, which in my opinion still needs further exploration. And this is very sensitive. If you dissipate too much, then you kill turbulence. If you don't dissipate enough, you get unstable. So it's really a very sensitive part of the whole framework. There is another plus of the kinetic representation that in turbulence modeling, instead of you generate higher order correlations, and who tells you what are the boundary conditions for a third order cumulant? It's a total nightmare. Here, believe it or not, you still work on the crystal I was showing before. So all the boundary conditions are managed in terms of mechanical operation between particles, so to say. And in a way, the boundary conditions are always realizable if you use the kinetic approach, which is by no means the case if you work with tensor instead of what I call multiscalars, because each population is a scalar. So the set of discrete population is a multiscalar. Multiscalar is a good object to work with, also because it allows you to design the boundary condition in a way that they are always realizable. So, I mean, again, as I said, I don't work on the subject for long, but the subject keeps going without me, happily enough. And I asked Kudong Chen, this is a courtesy of Hexa Corporation, and this is a talk they give in 2016, and you can see the kind of complexity. And if I think that we started with the flow past the cylinder, I cannot believe. Actually, I should tell something to the young people. With me, this whole business started as an exercise. I was at IBM to learn how to program IBM machines. And there was a paper on lattice gas automata by Tommaso Toffoli. Some of you might know him. It's called Cellular Automata for Supercomputers, which, by the way, didn't do hydrodynamics because it was using a square lattice instead of the hexagonal. And my boss stepped in and said, Sauro, why don't you look at that so that you learn how to program IBM machine, which I did, even in assembler, which proved really fun, but you just do once in your life. And when I think in those days, and now the thing solves this type of problem, I just cannot believe. So, and I think they're doing a lot of work with NASA, with NASA, actually. This company, which is now called, I think, PowerFlow is the name of the code by X, and now it's called PowerFlow Simulia. And just this is the reason why I screwed up my presentation, because I wanted to add the slides while I was watching the last talk, but the message there. I felt guilty that I didn't put any specific thought in terms of being useful to this community other than offering what we did. But I think, if I just can summarize, based on what I see so far, can we think of an astro very large eddy lattice boson? I would love to be working on that, really. I'm jealous. You have such a beautiful field. Mine is not bad either, I would say. But when I see the turbulence affect the way galaxies are formed, planets, it's just too beautiful. So no magnetic field in my talk. Magnetic field is no big deal. We know how to do magnetic aerodynamics since the early days, okay? Since day one, basically. Compressibility is an issue. Lattice boson is born basically non-compressible, weakly compressible. But EXA, precisely this simulation for NASA, they now can run on Mach 1. I heard this morning that there are problems with Mach 20. I don't think we can even dare to go in that direction. But Mach 1 you can do, provided, of course, you make your lattice a little bit more connected. But by now, the lattice boson community knows how to deal with that. We use them ourselves for problems in non-equilibrium soft matter, basically. So I think this is done. This is doable. Grid refinement, which I think you also use very heavily in astrophysics, is done, but not much in academia. It's very demanding, okay? EXA has it. Some group have the grid refinement, but is not really widespread. So if you can think of other items which are key for of course, subgrid modeling. When I asked what are the Reynolds number around, I was told 10 to 10. I was expecting much worse than that because an airplane has 10 to 8. So if I think of a galaxy, I was expecting 10 to 20. And then, of course, there is an enormous scope for subgrid modeling. Not that lattice Boltzmann would solve the problem, but maybe you can, I think you can extend maybe one more decade than using the standard, I mean, the Navier-Stokes approach to fluid turbulence. So I think, to summarize, I think there is a very sound notion. I mean, a very large area is, if you take the perspective of coarse graining kinetic theory, you are by definition free from scale separation issue, and this is a big, conceptually, it's a big point, because in practice, it allows you to handle non-equilibrium strain turbulence in complex geometries where you don't rely upon any symmetries as you do in most engineering studies. Another point I didn't stress enough, but in fact, I just told you that you don't have to solve for the Poisson problem. It means that you do not have the velocity pressure correlations, which are very global, and they are a source of troubles if you do, if you coarse grain the Navier-Stokes equation, because you have velocity and pressure. You work hard, you get parallel efficiency also in complex geometry. And there are subjects which need, in fact, to be developed. And I would say on demand. If you come with a specific problem in your community, I can think, I've been enjoying this for quite a while with other type of problems. Very likely, I think, for your problems, we will need to go to higher order lattice Boltzmann, or maybe invent new methods to solve kinetic equations. Some smart Monte Carlo. People in discrete velocity, I mean, people are smart, generally. I mean, that's, I see a lot of progress in many areas. So think, if you have a good method to solve a simple kinetic equation, let me know, because it could be of use, not necessarily lattice Boltzmann. This is a wild speculation, but I would say that if there is machine learning, everybody's talking about machine learning, maybe it would be interesting to see whether the machine can learn the turbostat instead of learning the turbulence model. The turbostat, I mean, machine learned kinetic equation for the turbulent eddies. So the theory is partially unsettled, spatially near boundaries, and as I said, for astrophysics, there are a few items which I think, I see definitely scope for interaction, but of course, nothing comes easy. It's all the items I see require a lot of work. Finally, this talk is really dedicated to Stephen Orszag, who unfortunately passed away a few years ago. He was a magnificent mentor and a dear friend. And I have to acknowledge, of course, Sudong Chen and Yakot, because I really learned a lot from them. And it's really, they were really very useful and very enjoyable colleagues and friends. So thanks for your attention. And I'm happy to see that this situation is slightly better than this.
Right, so we do actually have time for a few questions. So, yeah.
Saro, this is, of course, a challenging problem because partly the collisions. Oh, thanks. This is, of course, a challenging problem partly because of the collisional terms. Have you thought about whether an easier case that these methods could make an impact on might be neutrinos in cosmology, because those satisfy the collisionless Boltzmann equation, although some non-standard models do actually let them have collisions.
I mean, how could you pose that? This question is precisely what you're doing. I think there is a name who should be known here, Luciano Rezzolla. I think he got famous with the black hole. He asked precisely this question. We are working on that, but careful. There is one point, though. If you want to do the neutrinos, then you have to be collisionless. And then my building, then you cannot use, well, actually, you can, but let me go back to this expression. Sorry. Why I'm so, okay. There is a strong assumption here that you are close enough to local equilibrium that you can mimic the collisions through a relaxation. And in principle, BGK only applies for weak departure from local equilibrium. Now, very good point. Not true if you let omega to be an independent field. So what we are doing now for the cosmological neutrinos is to use high-order lattices where, in fact, I mean, that would be a long story. If I use many more discrete speeds, I can go higher up in the moment hierarchy. So how far can we go? And is that enough to describe collisionless neutrinos? We don't know. We are just running a test 2 months ago, and so far they are very encouraging. So we are precisely doing. Unfortunately, this is a sideline for me, but we have a student working on that, and I hope I can report some solid results if we meet again. So thanks for. But I mean, it's a conceptual twist because you have to go outside the collisional regime. So the question is, how many discrete speeds do you need to do that?
Any other questions? Yeah.
I guess I'm curious. So you can derive Navier-Stokes from the Boltzmann. Can you derive a Smagorinsky type model from this approach? This sort of seems like a hybrid between an LES and a RANS model right now.
Absolutely. Actually, you can do much better than that. There is a paper by Udong, myself, and Steve, but the credit is Udong. It's a JFM 2005 where we do precisely this. Not only you get Smagorinsky, you get what is called speciale. I don't know if you are, where you have a recirculation pattern. I mean, higher order, much more complicated than Smagorinsky. But, I mean, this is a subset of what I'm showing. I'm sorry, maybe I've been too quick. It's a subset because it's something that we derive on the assumption of zero temperature, if you want. So that instead of starting from Boltzmann, from the molecule, you start from a Eddy Boltzmann where you only have U prime and capital U. Okay? So it's not a double fluctuation theory, it's a single fluctuation theory. You do Chapman-esque on that, and you get precisely what you say. So it's really rich. It's really very rich.
Great. Let's thank the speaker again.
Thank you.
I would like to thank the organizers for invitation to participate here and for organizing a very nice, interesting workshop here. So we heard a lot about astrophysical turbulence today. And so in many cases, actually most cases, it is compressible. So we do need to understand what compressibility changes when we are interested in turbulent fluxes, how spectra behave, and actually which spectra we want to look at. Okay, and so the idea is to we still don't have any analogs of, or maybe until recently we didn't have any analogs of Kolmogorov's 4/5 law for compressible case, and so many of our astrophysical limitations are related to that missing bit. So I would like to talk today about filling that gap, basically, and I hope it will help people to choose right statistics to describe their simulations, and will help to guide observers to look at specific correlations in the sky that will help to get the physics of this turbulence. So. So the talk is, I will start, so this is my motivation. There will be a few theory slides. I will probably skip methods and discuss results from numerical experiments, which explain how this theory works. And then there is some papers. Supratik Banerjee was my collaborator theory-wise, and this group of people, Dima Kotov, Bjorn Sjogren, and Helen Yi, are helping with numerical methods here. So, so let's see. Starting from the very basics, so we have Navier-Stokes equations for the compressible case. So what differs them from the incompressible is, of course, density, which is now a free field to evolve, and also dilatational velocity component. So we have a new scalar field and a new vector field as well, in addition. Okay, so the pieces on the right-hand side, this is forcing, this is dissipation. I will not talk much about dissipation because I will present results from coarse DNS in this talk. basically, so dissipative terms will not be resolved on the grid. But forcing is kind of standard. I'm using large-scale forcing in three-dimensional turbulence simulations, which is stochastic, has finite correlation time. And so this acceleration, external acceleration A is computed according to Ornstein-Uhlenbeck process. We fix energy injection rate and scale of energy injection. And I will be talking actually about two different simulation types. So one would be three-dimensional simulations, and the second one would be simulations in 2 dimensions. So the forcing scale will be placed differently in those two cases. Okay, for simplicity, I'm using a very simple isothermal equation of state, but the formalism that we developed can be extended easily to a general case of the, for example, of the ideal equation of state here. And so besides this nonlinear term, which is preserved from the incompressible case, basically, the new nonlinearity can be potentially introduced by equations of state. But this case does not bother with that issue, okay? So that's the most simple one. So if we are looking at the isothermal system like this, equations 1 and 2, we have one of the invariants is total energy, and it's a sum of kinetic and potential energy. I would call this potential energy. This small e is sound speed squared times logarithm of density normalized by the mean. Okay, so I will be using a technique which is complementary to what Greg Eying is using. It's not coarse graining, but it's rather point splitting. And so the first question which appears in this problem, how do you point split this combination? Okay. It's not, none of these terms here is quadratic. They are becoming quadratic when fluctuations of density are small, but otherwise they are not quadratic. And so how do you split this between 2 points to find your structure functions or correlation functions? Okay, so there are, and this is the key, basically, it's easy to derive an exact relation for this compressible case, but the key is to find the right, to make the right decision while splitting those things. And so I'm tempted to say that we found the right approach here, because what we do, we point split momentum from velocity in the kinetic energy correlation function. And also we split density and the specific Gibbs energy in this case for the potential energy correlator. There were alternatives offered. For example, Steve Warzak and collaborators used to split this kinetic energy term symmetrically, so that you have a scalar product of velocity multiplied by square root of density, and then the same kind of thing on in front. So unfortunately, the mean value of that product is not 0, because this is not a conserved quantity. And so the idea behind this point splitting that we are using here is to always have at least one quantity here. In this case, this is momentum J, which is conserved, and density rho, which is also conserved. Okay. We tried a bunch of different approaches. For example, this internal energy in the case of general equation of state is sometimes split in the same way as here. So it would be sound speed times density dot sound speed, right? And so this, I can show that this is not working because none of those quantities is conserved. So then it means that this energy correlation function cannot be made it should be a symmetric cross covariance function. That means that both quantities should be properly centered. Okay. So in this case, in particular, it's rho is conserved, but it's not centered, right? And so that is the reason why we need two terms here. We need to decompose the background conditions from the turbulent fluctuations. So previous previous attempts to derive this relationship unfortunately failed because of the lack of this term. They forgot this and used 4 instead of 2, used 2 instead of 4 there. I think we fixed that issue, and many terms that were artificially present in the previous exact relations were dropped this way. They canceled out, basically. It's interesting that recently we found that the idea of available potential energy, which is basically this term present here, was introduced in 1955 by Lorentz. Okay, so as soon as we have these definitions, we can write down the scale-by-scale balance equations for the total energy correlator and for kinetic and potential energy correlators separately. So we have exchange terms here and there, which have different signs and cancel out when you sum them up. They don't show up in the balance equation for the total energy. And then we can take Fourier transforms of these guys, and we can come up with a standard relation with transfer functions for kinetic energy and potential energy. This is Fourier transform of dissipation and forcing. And we can define energy fluxes, spectral energy fluxes. The total flux includes 2 components, the kinetic one and potential one. And it can be computed as a simple integral over the transfer function, okay? And so then the assumption is that in the inertial range, these fluxes are constant. And so we claim that the theory tells basically that total energy flux should be constant, but we can also look at what happens to all these other fluxes. Okay, so so let me show just a little animation here. Oops. So it's a 3-dimensional turbulence in a box at Mach number of 0.6 roughly. What you see is basically clouds, and we know that in astrophysics, in the ISM in particular, we observe clouds. So even at those small Mach numbers, you see a cloudy structure. Okay, so if you look at the vorticity distribution at this Mach number, you see a lot of vortex filaments. You can zoom in and you can see real actual elongated filaments very nicely here. At the same time, because this is compressible turbulence, right, you see shocks. So these are shock surfaces present in the volume. So the shocks are patchy and at this Mach number, and they have this weird geometry. So we have basically we have a dominating incompressible part, the eddies, and shocks and acoustic waves present here. Okay. So if you look at the power spectra, and we talked a lot about power spectra here in astrophysics, usually you don't go beyond that. You see that even at 1,000 cubed at this low Mach numbers, so one line, this one, the blue one, is 0.38, and the other one is 0.57. You see, you don't really see a good scaling range. And this is the best method you can use. It's seventh order accurate in space and third order in time, very efficient one, by the way. And so what you see is a bottleneck on the right-hand side and pre-bottleneck or maybe trough in the spectrum here, right? So, so the very steep dependence of numerical dissipation on the wave number produces this effect here, okay? But overall, you expect to see a Kolmogorov slope at these Mach numbers. And that's what we see here, more or less. Okay, so now let's look at the fluxes that we just defined. So the black line is not seen because it's overlapping with the kinetic energy flux. So one means the energy flux is equal to the energy injection rate here. So what we see here is that energy is injected at large scales, and then it gets cascaded down the hierarchy of scales in such a way that the flux is constant. You can look at the internal energy, potential energy flux. This is the red line. It is really, really small. It's amplified by a factor of 100 here. You see it's not really constant in this case. And you can also look at the exchange term. This brown curve here shows it. It is varying close to the forcing scale, but then it's more or less constant after that. So if you, this is the low Mach number case. If you look at the larger Mach number case, you see that the same kind of nice flat part of the flux. You see that the red line, the potential energy flux, becomes really straight. Now this potential energy flux is larger than in previous case, so it's enough to multiply it by 10 so that we see it, right? And also the exchange terms, also it looks like they scale, they are roughly constant across this range of scales. We can look at different terms that enter that form the kinetic energy flux. So this is one of them. Again, here is a combination of, these are third order things, and these are correlation functions, and then you Fourier transform them to get pi k, okay? And so there are two things that are actually in the incompressible limit. They are equal to each other. But here we can see that they have slightly different slopes, and they are pretty close to each other. So that's the effect of compressibility. And they are close to 1/2. So when you sum them up, you get 1 again. Okay, as Mach number goes up, this same guys split a little bit more wider. But when you sum them up, you are still pretty close to the expected value of the energy flux. Okay, so now we can look at how at the details of energy. Oh, I will probably skip this. So this gives you details of the potential energy flux and exchange terms. So this is total exchange terms. These are two components. Actually, this green one corresponds to pressure dilatation. And at this level, it's pretty close to 0, basically. Because we multiply these fluxes by 100, so it's not clear whether it's numerical or whether it's non-zero here. It would be hard to find out. The same result for higher Mach number case. So now we can ask this question: what happens to the forcing? How do we are using this standard Ornstein-Uhlenbeck forcing, which everyone uses. So how does it affect the fluxes? And so that's the force as a function of scale. Okay. And so it's clear that this green line comes pretty close to the red line here. And so I'm claiming that the bump in the in the flux of potential energy is related to the forcing. It's a direct result of the forcing here at low Mach numbers. When the Mach number is higher, this red line becomes nearly flat because this green line then goes a little more below the red one. So the potential energy flux is larger at higher Mach number, and so the effect of the forcing is not felt. So now we can look at what actually forcing is doing there. And so there are two components for the forcing. One is looking at correlations of momentum and external acceleration. And this is this line. It doesn't have, it's very concentrated to the scale of where you force the flow. So it's basically zero otherwise outside that forcing range because this acceleration is very, very smooth. And so while momentum has a lot of structure. But the other one contaminates the potential energy flux in this case. Okay. Oh. Okay. Yeah. Okay. So let me show you just a few nice pictures. So this is two-dimensional cases. You see vortices and shocks, and it's from an 8,000 squared simulation. So you have shocks. Here you have condensate forming, and you have nice condensate vortex dipole here with shocks crossing the volume. But if you take a look at power spectra here before condensate forms, this simulation is forced at an intermediate scale here. You can see that the velocity spectrum is steeper than predicted Kolmogorov. This is because coherent vortices contaminate the inertial range here. And this is the spectrum of potential energy. They more or less go in parallel at large scales above the forcing scale, and then they change slope below.
So I want to leave time for the discussion.
Okay,
so
yeah, sure. Okay, so so let me just pop out the summary, and thank you for your attention.
So given the timing, I think we're going to jump straight into the discussion, and if there are questions that can come up then.
Okay.
Discussion by asking if there are any questions for Alex. Let's see. Is there one from the Zoom?
I have one.
Yes. Okay.
Actually, it's sort of, this is...
Introduce yourself.
Hi, this is Greg Einck. So this is actually something that I've discussed with Alex before. I'll just say it again publicly, which is this point splitting has mathematical problems for the compressible case that you and I have discussed before, which is that a priori, it doesn't remove all the Reynolds number dependence. I'm talking about the kinetic energy part. And I think this makes it a little difficult. I mean, of course, this could cancel when you do averages. I don't know, maybe it does. But a priori, there's residual Reynolds number dependence. Whereas Farisal and others have done the coarse graining analysis for the equations you consider, and you know there's no Reynolds number dependence. Don't you think you should really check to compare and make sure that they give the same results? Because at least the coarse graining analysis, a priori, you know, really removes all these ultraviolet divergences or Reynolds dependence.
Oh, Greg, thank you so much for this question. Yes, we discussed that. And I think we can. So what Feiraizel is using is a slightly different formulation of the equations, which is variational, as he says, right? And
Yeah, I
so
don't think the results don't really depend on that.
yeah, exactly. So the average, the spatial averages that we have in all those correlators, if they are written in the right way with test functions, I think your complaint should be removed. I actually wanted to discuss this with you here, hoping that you will come, but
I would have loved to do it.
but maybe we can talk on the phone. I have a counter question. So using this point splitting technique, we bumped into this big question, maybe not so big, but how to point split, right? And I wonder if you guys with coarse graining have the same sort of problem, because it is clear from the experience I have with numerical data and different point splitting decisions that some of them just fail miserably, just simply do not work. Because a lot of energy of fluctuations is lost in this analysis.
Could you define what point splitting means in this context?
Point splitting, it's a regularization technique which relies on point differences or two-point correlations. Okay.
Okay, rather than
So like
averaging over
structure
scales.
functions and yes.
Okay.
So point splitting, you want to work with averages of products or differences between 2 points, and this comes power spectra come from there, structure functions come from there, all classical Kolmogorov stuff comes from that end. So my question to Greg is. If you guys can split the kinetic energy, so right now you do it like mean density times square of Favre averaged velocity, right?
Yes.
So if you do it like mean momentum times mean velocity, would it be different? Would it incur some problems in the formalism? And there are, of course, myriads of other ways to do that. So in your talk, you presented these nice slides with yellow fonts and red fonts, but you did not discuss that decision, which is important, I think.
Well, I mean, I guess there's not any real decision on our part because we just coarse grain the basic conservation laws, and then you have whatever is sitting there. I mean, the mass density equation contains rho, the momentum density contains J, right? So we don't have to choose. I mean, the choice is thrust upon us, and it works. I mean.
No, formally, I would love to really to see the basically simulation results analyzed in the way that you propose. That would be a good test bed for that.
So while we've got
Yeah.
Greg, okay. While we've got Greg on the line, Yuan had a point that I don't think actually got fully resolved, of how you can assume the cooling to be a large-scale action, particularly because it's a density in the ISM. It's a density squared quantity because of atomic cooling is a collisional process. So that's inevitably going to act on the densest regions, which tend to be very small scale.
Well, I don't know. I guess the question is ultimately sort of how you balance the cooling rate versus the local eddy turnover rate, right?
Mm-hmm.
And what Lithwick and Goldreich had analyzed was sort of metal line transitions, and their estimate was that if you look at the scale at which so basically if you go to really small scales, how fast is that cooling rate compared to the eddy turnover rate. At sufficiently small scales, the eddies turn faster. And so the cooling doesn't affect the turbulent dynamics unless you go to sufficiently large scales. And so the question is the rate versus the local turnover rate, right? I mean, that's the distinction.
Shmuel, you wanted to?
I would just add that that's basically what we astronomers call the cooling time, which for the CNM, for the cold neutral medium at 100 K would be about 0.3 parsecs.
The cooling length.
Yes.
The length below which...
That's just you take the lengths, multiply by the sonic crossing time, if you like turbulent time, but the Mach numbers are not huge, so it's not a huge difference, at least not in our of the order of magnitude estimations of astronomers, and compare this with the cooling time.
Yeah, that's comparable to the estimate that Lithwick and Goldreich made. I mean, they said of the order of 0.2 parsec.
Okay, good enough for us astronomers.
So again, the point, that sort of is the cooling scale that I was discussing. And then the question is whether that is much larger than the rate, the length scale at which entropy is being produced.
Which is going to be some sort of shock thickness, and that's also a few tenths of a parsec in the ISM, so maybe not. However...
So, Greg, I have a related question for you regarding the physics here. In your initial slides, you talked about the divergences and got into the regularization of that. And that was all very interesting mathematically, but divergences are divergences, and that's either telling you that there's a real divergence or that your equation is somehow breaking down. And I'm assuming here it's the latter, but can you tell us more about the physics that's making these equations actually break down on very small scales?
As far as we know, taking incompressible Navier-Stokes, there's no limitation on the Reynolds number for incompressible Navier-Stokes. I mean, this is an somewhat open issue because we don't really know whether those equations develop singularities.
Yep.
But there is mathematical results for lattice gases that say that even if you develop a singularity, a weak solution of Navier-Stokes equation is still the correct physical description. And so there's a nice, this has been actually proved for both Boltzmann equation and also for some lattice gas models, that if you're considering the small Knudsen number limit and also a small Mach number limit, so incompressible equations are valid, then even if there's a Leray singularity, the incompressible Navier-Stokes equation is still valid. And the point then is that those singularities are very sparse in space-time. And so in the sense of weak solutions, it's like, you can have a shock and that doesn't mean you have to throw away the Euler equation because the shock is only on a hypersurface.
True, but
so
you don't have infinite density in the shock, and in the actual world, other processes will come in.
Right, but I'm trying to make an analogy. For the incompressible Navier-Stokes equation, we have rigorous results for Boltzmann and also for some lattice gas models that say that even if you have these crazy Leray singularities that nobody's ever seen, the equations that you start with are still okay. And I don't know that such a thing has been proved for compressible Navier-Stokes or compressible MHE. In fact, those are very simplistic models of the interstellar medium, right? I mean, it's there's actual multiple species,
multiple phases,
anisotropic transport coefficients. I mean, you name
gravity.
Gravity. Okay, yeah, keep adding it on. But the basic ideas of the analysis still carry over. Then there are complexities that you have to address. I guess my most basic point was you can do the same analysis as I did in my talk, as I sketched in the talk, even starting off with the kinetic description. So, you don't have to go and start at the fluid level. You can start at the kinetic equations for a weakly coupled plasma.
So this brings us to what seems to me one of the dominant topics that we've been discussing, which is how do you go from an idealized description of a uniform fluid, maybe isothermal turbulence, to at least in the astrophysical case, but I think also in other fields where you have complex multiphysics flows. And I think this is also true in the biophysics case, where it's not just an isothermal flow. You have things embedded in it, or you have a thermal structure that will give you a multi-phase medium so that you have very dense things trying to interact with very rarefied things. And in the astrophysics case, you have gravity that can decouple the dense things from the surrounding rarefied flow. Anybody want to pick up on that comment? Yes.
I want to talk about some observational technique based on this multi-phase gas in both molecular cloud in our galaxy and also in cluster galaxies, that the talk given by Yuan. So in the molecular cloud gas, there's a dense cores, and people find that when they trace the motions of dense cores, they gave the velocity spectrum, which is consistent with the Kolmogorov spectrum that we expect for the molecular cloud. And in the Yuan's observations, that we also found that this H alpha gas also quite trace well the surrounding gas motions, like this kind of power law spectrum. And also, for example, the case of cold H1, cold neutral medium embedded in the warm neutral medium, and people found a good coupling between this cold gas and warmer gas. So, I mean, in a sense that it gave us a different observational techniques in different environments to study the turbulence in different phases.
Yuan?
I can add a little bit.
Let's see, wait till it comes on green. Oh, okay, go.
So I'm glad nobody forced me to show the analysis of my own simulations, and I would have to plead the Fifth Amendment because, like you said, you would expect gravity to cause the cold phase to decouple from the hot phase, and that's sort of what's happening in my simulations. And oftentimes people would describe the cold clouds as being ballistic, and what that gives you is actually a different velocity structure, structure function than what I had measured using the real data. And so somehow in the real universe, the cold phase seems to be well coupled to the hot phase.
Or are we looking at the surfaces?
But remember, I also had the CO measurement. And it
but
was
even CO becomes optically thick at very low densities compared to gravitationally bound objects. Blakesley.
Yeah, I would kind of agree with what all three of you have said. I mean, what we find in local interstellar clouds is that in the more diffuse regions, so traced by H1, H alpha, diffuse CO, the spectrum looks consistent with what you would expect given the temperatures and the same type of turbulent velocity. But where you get into, and I agree with Mordecai on this, on a decoupled flow is when you start to really trace dense gas. Self-gravity becomes important, and then it changes all your 2-point statistics, your 1-point statistic. It starts to look like gravity dominates the picture.
Right, and at that point, in Shira et al., we actually showed that you start getting these weird inverted spectra with most of the power at small scale instead of large scale.
Yeah, we also see that in our simulations. Exactly.
Right, because the gravity is producing very small scale structure.
Yeah, so you get actually a power law that rises rather than
exactly. Increases. But that's going to be very difficult to trace observationally because you're going to have to go to very high density tracers and still get coverage so that you get a range of scales. You and then Shmuel?
I just wanted to ask the question, like, how do we know in astrophysics what the kind of first order approximations for these molecular clouds are? So you would include more and more of these higher order terms as you think is fit to include them. Like what kind of question do you want to ask your simulation? But I've always thought like to first order these molecular clouds are isothermal, MHD. You have some guide fields and this has always been the way that I've thought about molecular clouds.
Well, the key point is they're self-gravitating. They form stars.
Yes.
So in some sense, the first order question we're asking is, how does star formation proceed under the influence of gravity with all those other physics that you've mentioned? Yeah. Shmuel.
So I'll just directly comment on that.
Is your mic on?
Yes.
Okay, great.
So, and as also I told you earlier, so usually my approach is to simplify things first and then to go to the all physics. So we have the multi-phase cold and warm, and now you also want to add gravity, which is present, obviously, but it's better to take it step by step. And for this, I'm asking Alexei. Alexei, are you here?
Alexei is paying attention
Yeah,
to something else.
so for this we can use simulations, and before we turn on gravity, just have simulations with hydro but also with in active cooling, so you have the two phase, and then the question is how the structure function looks like, and instead of just either thermal or a different equation of state, but now with active cooling where you have cold and warm and thermal instability, now how things look like, structure functions for velocity and density, and only then, when we understand this, turn on gravity and go further.
This is a great question, I think. So we've looked at this in 2004 and in 2013. So what you do is you do conditional averaging. So for example, you want to look at the structure function of velocity and how it scales, right? So you say, okay, give me the average of delta U in such a way that both points are sitting in the cold phase. So this will give you a very nice scaling of L to the 1/2, telling that this cold phase is basically supersonic. If you do the same exercise for warm points, you get Kolmogorov 1/3 very nicely, there's a lot of confidence. So this is a classical, I think, typical astrophysical non-homogeneous case where you have two phases. So your turbulence is inhomogeneous. If you want to use homogeneous tools to quantify it, right, you have to use conditional averaging. This is fine. It works like charm.
In some sense, that's what observers are doing necessarily. Because if you observe in a single tracer, you're observing typically a single phase. And then when you start taking your structure functions in that tracer, you're doing what Alexei would call conditional averaging. What's that? Well, each one can have multiple phases. This is true. And then you have confusion issues, and you're not doing conditional averaging. There was a question. Yeah, that's okay.
Yes, actually we encounter this kind of situation in galaxy clusters when we were looking at cosmological simulations of hot X-ray gas. In cosmological simulation, we have this thing called substructure. These are small dark matter halo, which contains its own density structure within the bigger density structure. So these are gravitationally stratified atmosphere, and you take these radial ring, and we look at probability distribution of density and temperature structure, actually in density structure in particular. And it consists of two parts. One is the log normal parts, which looks more like a homogeneous turbulent kind of thing that exists in cosmological simulation, but there's also a tail, high density tail, which is remnants similar to sort of these cooling high density gas that might be present in molecular clouds.
What's seen by, say, Kyne-Leinen et al.
Right, they are there, of course, in cosmological simulation of galaxy cluster formation. So we develop a very simple clipping technique. Just take the log normal Gaussian part. They behave very kind of like, they're similar to sort of turbulent medium, but the high density parts has to be taken separately. So when we compute the turbulent motions, or we can't just take the whole thing. You need to do the decomposition of nonlinear parts versus log normal parts, and then treat them separately. So this is it's very hard to do observationally, but in simulations, this is something that we have started to do, and that gave us a lot of ideas. In terms of taking average of density field is very dangerous because of the high density tail. So we're taking medium value, which usually gives us a pretty good estimate of average volume filling factor phase, and then this gives us a density profile. So I think in the galaxy cluster community, we're learning how to do the decomposition in presence of like Chandra observation with 1 arcsecond resolution. One can do this type of decomposition by identifying these little clumps, high density peaks, And so this is something that's still kind of ongoing, developing, but maybe there's something that we can share between different fields.
Yeah.
Very interesting what you're saying. Normally, I think in turbulence, we think of log normal as generated by collisions and shocks, and I'm assuming you mean the log normal here is generated by essentially gravitational friction. But Blakesley has made a nice model where she has a log normal and then at higher density a power law tail, and I'm wondering if now that could be folded back into modeling the PDF for this stratified structure of the subhalos you're talking about.
Yeah, I might actually, that's sort of what I was just talking about. Maybe that the same tool actually might be applicable directly in galaxy clusters as well. Maybe something we can discuss.
I think we're out of time. Does anybody have a last urgent comment? Otherwise, thank you all for your discussion.